Okay, so today we are working with rational equations. And so what we were working with before were rational expressions. Like we didn't have any equal signs in our problems. Now we're going to have an equal sign in our problem. So just to start, has anyone tried actually graphing any of the expressions we've been working with? No? Okay, so in Y1, I would like everyone to graph this. So how to put it in your calculator, if you watch what I do, we need 3 x plus 1 in brackets. Okay, so wherever I have brackets, you need brackets too. That's one of the things with these types of problems, is that you have to make sure that your numerators and denominators are going to remain separate, right? Yeah, so if you see I have like 3 slash. It's like the divide sign. The divide sign will give you that. Just like I have here as well.
Oh man, it's like a racetrack.
Okay, so Josh, you do super quiet, like a church mouse. Okay. Okay, so when you have this, if you hit graph, you'll get something that looks like this. If you have a newer calculator, so if you have one of the newer ones, it might not show you these lines here. Okay. So if you have an error with your window range, just go to your windows and change it all to -5s and 5s, like that. So your x and y minimum are both -5, because I want to be zoomed in a little bit. Okay. And so you can draw a little picture like I am, just like that. Okay. So if we were to look at this equation here, this 3 over x plus 1 plus 1 over x minus 1, what would our non-permissibles be? Exactly, right? And then if you look at your graph, you'll notice that these lines here are at +1 and -1. So these lines here are not part of our graph in the same way that the rest of the lines are. These lines are showing us where our non-permissibles are. And so if we were to extend our graph, this part where I'm drawing in blue, forever and ever and ever, it would never touch our non-permissibles. It would never touch that red line. Okay? So just like when we were first learning about non-permissibles, and I said x can be anything but those non-permissibles. So x can be absolutely anything except 1 and except -1. And we can see that on our graph. We can see x will get closer and closer and closer to 1 and -1, but it will never get to that point. Okay? And so these lines here are called asymptotes. And now the shirt makes sense, right? The graph will never touch the asymptote. Okay? So these graphs are kind of cool because they can actually show you our non-permissibles and show you that the graph will never actually be there. Yeah, the red lines are the asymptotes. Okay, so maybe I'll write. Okay, if you have a newer calculator, it actually doesn't show you it, but your graph will keep the same shape where you can see that the graph kind of converges to a certain point. Okay, and I'll label this as asymptote. Okay, so if we have something like this equation here, where we have this entire thing is equal to 0. When we're solving this, we would solve it just like if we had a quadratic that was equal to 0. So you could put y2 equal to 0. So I'll do that here. Just like this. Oh, did I say 0? Yes, y2 equal to 2. Sorry, good catch. Sorry, YouTube. Okay. And this is where we get, okay, so y is equal to 2. And so then we can solve it just like we would if it was a quadratic, right? If we were asking for it, you'd say, oh, I'd find the intercept, just like I always have. And where the graphs cross at the intercepts would be our solutions for x. Okay? So you'd go second trace 5, enter, 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 and you find for one of them, it's 0. And then for the other one, same thing, just like we always have. So the one thing that's a little bit different is when you're scrolling, because remember, you want to get, for the second intercept, you want to get really close to it before you find it. When you scroll, your little blinker will eventually just jump over the asymptote. So just keep going until you see that it's jumped over it. And there we go. So we can go like this. Enter, enter, enter. And we find that our other one is x is equal to 2. Okay? So even though we're looking at a type of graph we've never looked at before, the way we would solve it graphically is the exact same as for quadratics, right? We just use the intercepts, just the same way. Okay? The other way we can solve it graphically is we know a lot of people like to use the X Intercept method. So it's the same thing with quadratics. If we had like x squared plus x plus 3 is equal to 1, some people would do it where they put y1 is this and y2 is this. But we also talked about how you can make it, oh, minus 1, x squared plus x plus 2 is equal to 0. And then you find the x-intercepts, right? We can do the same thing with these problems. So if we were to make y1 all of this, but also add a minus 2 at the end, and then make your y2 equal to 0. So we'll go like that. And you hit graph. And I'm a pretty good artist. Okay? And then you can just go, okay, well, we know that we can find our x-intercepts the same way we always have. So intercept, enter, enter, enter. Oh, our answer is 0, which is good because it's supposed to be the same answer as before. And the same thing, second trace intercept. Move your little blinker all the way to the other one, like that. And then you get x is equal to 2. Okay? Because we put a negative 2, right? So everything was actually shifted down 2 points. Okay? So in both of these, for our solutions, we get that x is equal to 0 or 2. X is equal to 0 or 2. Okay? So like I said, even though the graphs look different, our method and how we solve them has remained the exact same. Just pretty slick. Okay, so let's flip over. So just like in quadratics where we learned how to solve graphically, we also have to know how to solve them algebraically. So there's kind of 2 different methods. The first is if your equation has one term on each side, they want us to cross multiply. So right here where it says, if it consists of a single expression on each side, cross multiply. And I find their notes in this section really wordy, so just take your pencil and write, if one term on each side cross multiply. Okay? And so we'll do an example of this as well. So if we go down to example 1b, this is what I mean by one term on each side. We have one rational expression here and one rational expression here. Okay? So we'll say one term cross multiply. I mean, like, we could put brackets around this like that. One term, okay? On either side of the equal sign. Yes, Shannon? Yeah? Everything can be expressed as a rational, right? Like 4 over 1 or 7 over 1. You can make a whole number expressed as a rational expression. Okay, so okay, so let's focus. Andrew, focus. Okay, so when we cross multiply, Justin, you should open your book. Okay, so when we cross multiply, all we have to do is multiply by the opposite denominator, right? So we just go 5 multiplied by x plus 2 is equal to 2 multiplied by x plus 1. Okay, and then we get to distribute it like that. And we get 5x plus 2, 5x plus 10 is equal to 2x plus 2. And then we want to solve for x. So we'll subtract 2x from both sides. And we want to isolate the x, so I'm going to subtract 10 from both sides. And we get 3x is equal to negative 8. X is equal to negative 8 over 3. Okay? No. I just did it because my personal preference is to try and keep this positive. But if you went the other way, you'd get negative 3x is equal to positive 8, so you'd get the same thing. Okay? So one thing about these problems is that you always have to verify your answers. Okay? So we do this just like we did with extraneous roots. We just take our x and put it back into the equation. Okay? So we go 5 negative 8 over 3 plus 1 is equal to plus 2 all under 2. Okay? So that gives us 5. And this is all stuff you would do in your calculator, but I'll write it out a little bit longhand. 5 and 3 is equal to 2. Negative 2 over 3. So we get negative 3 is equal to negative 3. We go sweet. Okay? So this is the one type of question where we have one term on each side, one here and one here, and we can just cross multiply. So it's pretty easy peasy. Okay? The other type of problem is if there's more than one term on each side, in which case they want you to multiply each term by the lowest common multiple of the denominators, which basically means if more than one term multiply by the LCD. Yes, Aaron? Pardon? So if we look at example 1a, that's one of these types of problems. Andrew, should be paying attention. Okay. So you can see, oh, we have two terms here. We have this one and this one. And we have two terms here. So we know that we have to find our lowest common denominator. So because we know this is the same as 4 over 1 and 7 over 1, who would like to tell us what our lowest common denominator is? You got it, it's x. So this one's a nice question actually because it's pretty easy. So they just say multiply everything by that. So we go this multiplied by x, this multiplied by x, x, and x. See? Just in the numerators. Because we have an equal sign, we are allowed to multiply things straight across the numerators. Okay? So we get 4x plus 2x over x is equal to 7x plus 3x over x. So right away, we can cancel these out. Okay? And then we get 4x plus 2 is equal to 7x plus 3. Okay? Okay, so at this point, we get to do exactly like we did before. We want to gather our like terms and solve for x. So I'll go minus 4x, giving us 2 over 3x plus 3. Subtract 3 from each side. Giving us negative 1 is equal to 3x. Divided by 3. So we get x is equal to negative 1 over 3. Okay? And then we get to verify it. So we get 4 plus 2 over negative 1 over 3. It's equal to 7 plus 3 and negative 1 over 3. Okay? That gives us 4 minus 6 is equal to 7 minus 9. And negative 2 is equal to negative 2. Which is awesome. Okay? So the one other thing to note is that you always want to kind of keep your eye on your non-permissibles, because when you're verifying your solution, the solution cannot be a non-permissible. Okay? Because we already know, like when we started this unit a couple weeks ago, we learned those x can be anything except those non-permissibles. So if you get a non-permissible as a solution, you should really be checking over your work. Okay? So that's a big hint to yourself that something has gone awry. Okay, so let's do, we're going to do both of these. Okay, so if we look at example 2a, which method would we use? Would we use the lowest common denominator or the cross multiply? How many terms do we have on each side? Okay. So I'm glad that someone said 4, because when we look at these terms, we want to look at them as like a whole rational expression. So within here, we have 2 terms here and 2 terms here. But if we look at it as a whole rational expression, we'd say it's like 1 term. Okay. So because we have 1 whole term, 1 rational expression on each side, we cross multiply. Which is awesome, because personally I find that's the easier of the two, usually. You got it. Okay, so we get What am I doing? No, I did it wrong. You should have caught me on that. Sure. Okay, so actually, I'm glad I did that, because then now you guys will not make this mistake ever. You always cross multiply like that. Okay? So, multiply that one by 3x plus 5, and then we get 6x minus 1 and 2x plus 3. Okay, so when we FOIL it, we get 12x squared plus 20x minus 6x minus 10. And we get 12x squared plus 18x minus 2x minus 3. Yes. Okay, so that works out really well for us, because then when we move all of our x's to one side, our x squareds will cancel out. Okay, so we'll get 2x, or actually, we have 20 minus 6. So you can combine like terms first, which is what we should have done. Reduce